The topic of this lecture is gravitational wave sources. One source of gravitational waves is the in-spiral and collision of two black holes or two neutron stars. Gravitational waves from these sources have been detected by the ground-based detectors LIGO and Virgo. The proposed space-based detector LISA should be able to detect the in-spiral and collision of white dwarf binaries as well. Other sources of gravitational waves that we hope to detect in the near future include supernova explosions and stochastic waves from the Big Bang. These are all astrophysical sources of gravitational waves, but in fact, gravitational waves are produced in any event that involves an asymmetrical acceleration of masses. So, for example, every time you wave your arms or jump up and down, you produce gravitational waves. Of course, these waves are too weak to be detected, which is why our current gravitational wave detectors are designed to look for astrophysical sources. In this lecture, I'll consider the production of gravitational waves from sources that are nearly Newtonian. That is, sources that are weak and slow-moving. Sources that have strong gravitational fields and fast motion such as binary black hole collisions, require the use of numerical codes to solve the full nonlinear Einstein equations. Before I get into the details of these gravitational wave sources, I need to review and extend some of the results on linearized gravity and gauge conditions. This is material that I covered in lecture number 32. The linearized Einstein equations are obtained by assuming the gravitational field is weak and writing the metric as eta mu nu plus h mu nu, where eta mu nu is the flat Minkowski metric with a flat background, and h mu nu is the metric perturbation. The linearized Einstein equations are 1/2 partial mu partial alpha h bar alpha nu plus partial nu partial alpha h bar alpha mu minus partial alpha h bar mu nu minus eta mu nu times partial alpha partial beta h bar alpha beta equals 8 pi times t mu nu of eta. Recall that h bar is the trace reversed metric perturbation, so h bar mu nu is equal to h mu nu minus 1/2 eta mu nu times h alpha alpha, the trace reversed perturbation. The left-hand side of this equation is just the linearized Einstein tensor, which I often denoted in previous lectures by GL for linearized, mu nu of eta and h. So this is the linearized Einstein equation. And notice on the right-hand side we have the stress-energy-momentum tensor, which depends on the metric, which is evaluated at the flat background, and it also depends on matter fields. And we're assuming that the stress-energy-momentum produced by those matter fields are small. Now we impose the Lorentz gauge, which is partial alpha h bar alpha beta equals 0. This just corresponds to a restriction on the coordinate system, which we can always make. Recall that the coordinates that satisfy the Lorentz gauge are not unique. Later, when we specialize to gravitational wave solutions, we'll place a further restriction on the coordinate system by imposing the transverse traceless gauge conditions. The linearized Einstein equations are especially simple in the Lorentz gauge. Partial alpha h bar mu nu equals minus 16 pi t mu nu. Each component of the trace-reversed metric perturbation, h bar, satisfies a flat space-time wave equation with source proportional to the stress-energy-momentum tensor. Also notice that we can act on this equation with partial mu, and because the partial derivatives commute, the left-hand side vanishes by the Lorentz gauge condition. And this implies that partial mu t mu nu of eta is equal to 0. This is, of course, just the linearized version of the statement of local energy-momentum conservation. In the region of spacetime near the source, the solutions for h bar mu nu can be rather complicated. Recall that mass can produce static or quasi-static 1 over r-type fields in and near the source. But far away from the source, the metric perturbation transitions to a wave solution. I showed in an earlier lecture on the linearized Einstein equations and gauge conditions, that would be lecture 32, that the general wave-like solution in Lorentz gauge has the following form. H bar 0, 0, that's the time-time component of the trace-reversed metric perturbation, and it's a function of the spatial coordinates x vector or xyz and the time coordinate t. This is equal to the real part of the integral d3k of k hat I, k hat j times an amplitude aij, which can depend on the k, times e to the I k vector dot x vector minus omega t. The time-space components of h bar are given by the real part of integral d3k k hat j aij, the same amplitude, times e to the I k dot x minus omega t. And the space-space components are h bar ij of x and t equals the real part of the integral d3k aij of k e to the I k dot x minus omega t. The notation here is that k vector, or ki, is the wave vector, and omega, the angular frequency, is just the magnitude of k vector, the wave vector. The unit vector k hat is just k vector divided by omega, And when I use index notation, I leave the hat on k hat. So k hat I is just ki divided by omega. Now let's impose the transverse traceless gauge conditions. In other words, we want to transform the metric perturbation in Lorentz gauge, which I call h mu nu bar, to TT gauge, which I'll call h mu nu TT. In previous lectures, I used a prime to denote the transformed metric perturbation instead of TT. So this was h mu nu bar prime in previous lectures. I'll express this transformation in terms of the amplitude A. So Aij is the amplitude in Lorentz gauge, and Aij TT is the amplitude in the transverse traceless gauge. The relationship between these amplitudes is given by Aij TT is equal to Aij plus k hat I times I omega Cj plus k hat j times I omega Ci minus delta ij times I omega C0 minus k hat k times I omega Ck, where I omega C0 is given by minus 1/4 times A kk plus k hat k, k hat l times A kl. And I omega Ci is given by 1/4 times k hat I times A kk plus k hat k, k hat l, A kl minus k hat j times A ij. Now the metric perturbation in TT gauge is just given by the amplitude in TT gauge through the usual integral relationships. In other words, h bar 0, 0 TT is the real part of the integral of d3k times k hat I, k hat j times A ij TT times the exponential factor e to the I kx minus omega t. And h bar 0I TT is the real part of integral d3k k hat j aij TT times the exponential, and h bar ij TT is the real part of integral d3k aij TT times the exponential. Now it's not difficult to show, using the explicit expression for the amplitude in TT gauge, that the time-time component of the metric perturbation vanishes, and also the time-space components vanish. And for the space-space components, they're trace-free, so that's the traceless condition. And they also satisfy partial I h bar ij TT vanishes. This is the transverse condition. The question I'd like to address now is, how are the space-space components of the trace-reverse metric perturbation in Lorentz gauge related to the space-space components of the metric perturbation in TT gauge? In other words, if we know the metric perturbation in Lorentz gauge, how can we efficiently compute the metric perturbation in TT gauge? The first step is to rewrite the relationship between the amplitude in Lorentz gauge and the amplitude in TT gauge. I'll leave it as a practice problem for you to show that Aij TT is equal to Pik Pjl times AKL minus 1/2 Pij Pkl AKL, where Pij is defined by delta ij minus k hat I, k hat j. This tensor P is a projection operator that projects into the direction orthogonal to k hat, the direction of propagation of the wave. So P gives the transverse projection. In this expression, PIK PJL times AKL is just the transverse part of the amplitude AKL, and this term removes the trace. From this result, we can write the space-space components of the trace reverse metric perturbation in TT gauge in terms of the amplitude in Lorenz gauge. The result is h bar ij tt, which of course depends on x and t, equals the real part of the integral d3k times pik pjl minus 1/2 pij pkl times the Lorenz gauge amplitude akl, which depends on the wave vector k, times the exponential factor e to the I k dot x minus omega t. To see how this result can be used in practice, let's assume that the direction of propagation is in the z direction. Then the unit vector k hat can be written in index notation as delta I3, and the projection operator Pij is delta Ij minus delta I3 delta J3. Now it's not hard to see that this is equivalent to delta I1 delta J1 plus delta I2 delta J2. So a convenient way to write this projection operator is delta IA delta JA, where indices like A and B range over 1 and 2, in other words, the x and y directions. With this result for the projection operator, our expression for h bar ij, the trace reverse metric perturbation spatial components in the TT gauge, is the real part of integral d3k of delta IA delta KA delta JB delta LB minus 1/2 delta IA delta JA delta KB delta LB times the Lorenz gauge amplitude AKL times the exponential factor e to the I k dot x minus omega t. Notice that in each of these terms we have a sum over the repeated index A as well as a sum over the repeated index B. Also notice that the assumption here is that each of the modes in this sum over k, each of the modes propagates in the z direction. As a result, all of these projection operators in parenthesis are independent of k, and we can pull them outside the integral. This gives delta IA delta KA delta JB delta LB minus 1/2 delta IA delta JA delta KB delta LB acting on the integral over k of AKL e to the IKX minus omega t, but that's just the trace reverse metric perturbation in Lorenz gauge, so that's just h bar ij. And this simplifies to delta IA delta JB times h bar AB minus 1/2 delta IA delta JA times h bar BB. Now notice that if either of the indices I or j is equal to 3, in other words the z direction, then the right-hand side here is 0. So h bar 13 tt and h bar 23 tt and h bar 33 tt are all 0. Now if I and j are both equal to 1, we find h bar 11 tt equals h bar 11 from this term minus 1/2 the trace in the transverse directions of h bar, that's h bar 11 plus h bar 22. And likewise, h bar 22 tt is equal to h bar 22 minus 1/2 the trace, h bar 11 plus h bar 22. And of course, these expressions simplify to 1/2 h bar 11 minus h bar 22 and 1/2 h bar 22 minus h bar 11. And finally, h bar 12, transverse traceless. Notice this term vanishes if I is 1 and j is 2, and this term just gives h bar 12. Also recall that for the trace reverse metric perturbation in TT gauge, if any of the indices are equal to 0, then the result vanishes. So h bar 0, 0, h bar 0, 1, these are all in the TT gauge, h bar 0, 2, and h bar 0, 3 all vanish. You can see from these explicit results that, as expected, the trace reversed metric perturbation in TT gauge is trace-free. And this implies that the metric perturbation itself is equal to the trace reversed metric perturbation. There's no difference when you reverse the trace because the trace vanishes. And this tells us that in our previous results we can drop the bars on h bar mu nu tt. So what we find is that for waves propagating in the z direction, the spatial components of metric perturbation in TT gauge are obtained from the trace reversed metric perturbation in Lorentz gauge by h13 tt equals h23 tt equals h33 tt equals 0. h11 in the TT gauge is just h bar 11 minus 1/2 h bar 11 plus h bar 22. h22 in the TT gauge is just h bar 22 minus 1/2 h bar 11 plus h bar 22. And finally, h12 in the TT gauge is just h bar 12. Notice that the right-hand side only depends on the transverse components of the trace reversed metric perturbation in Lorentz gauge. In other words, it only depends on h bar 11, h bar 22, and h bar 12. So we can essentially throw away the remaining components of the trace reversed metric perturbation in Lorentz gauge. From this example, we can now write down the general prescription for obtaining the transverse traceless metric perturbation from the trace reversed metric perturbation in Lorentz gauge. To obtain Hij Tt from h bar mu nu for gravitational waves propagating in a single direction. The first step is to throw away the 0, 0 and 0i components. The second step is to throw away the longitudinal components. In other words, the components of h bar mu nu in the direction of propagation. The third step is to remove the trace from the transverse components. And finally, we leave the off-diagonal transverse components alone. This prescription is useful in practice because, as we'll soon see, the linearized Einstein equations are easy to solve in Lorentz gauge. And far from the source, our assumptions hold. Namely, the solution is wave-like, and the waves propagate in a single direction. Just to be clear, let me draw a picture. Here's the source, and we're interested in the gravitational waves far away, so at some point in space, here are the gravitational waves passing by. And all of these wave modes travel in the same direction, namely the radial direction. So k hat equals the radial direction. And the final point, explaining why our prescription is useful, the gravitational waves are expressed most simply using the TT gauge. As we analyze gravitational wave sources, it's useful to categorize the types of sources by the approximations needed. Starting with the most restrictive case, we have weak, slow-moving sources with negligible internal gravity. For example, a rotating rod. So here's the rod with length L, and it's rotating with an angular velocity of omega, and we assume this is a weak source of gravity, so that gm over c squared is much, much less than L. In other words, the size of the rod is much greater than the Schwarzschild radius of the rod. We're also assuming slow motion, so omega L is much, much less than c. We're also assuming negligible internal gravity. This means that the mass of the rod is sufficiently small that it can be held together by its own internal stresses. That is, the gravitational attraction between different parts of the rod can be ignored. This can be quantified by assuming that gm squared over L squared, which is the gravitational force between different parts of the rod, is much, much less than the centripetal force, m omega squared L. By the way, it's a simple exercise to show that these two assumptions together imply that gravity is weak. The second type of source that we can consider is weak and slow-moving with non-negligible internal gravity. For example, a binary star system. So here we have two ordinary stars orbiting about each other with some angular velocity omega and separation L. Here we assume that gravity is weak and the motion is slow, but we can't ignore the internal gravity. It's the internal gravity that holds the stars together and keeps them in binary orbit about one another. Now, case number 3 is strong, slow-moving sources. For example, a binary black hole or neutron star system where the two objects are in the early stages of in-spiral, so they're still far apart, and moving slowly. The fourth type of source that we can consider has strong gravity and fast motion. For example, the final stages of binary black hole or binary neutron star mergers. My plan for the remainder of this lecture is to treat the first case in detail. That's the case in which gravity is weak, the motion is slow, and the internal gravity is negligible. Now, the result of this analysis will be a formula for the gravitational waves, that is, an expression for the spatial components of the metric perturbation in TT gauge in terms of the source motion. It turns out that this same result also holds for the second case. This is the case in which we have weak gravitational fields in slow motion, but the internal gravity is not negligible. Even though this final result for case 1 and case 2 is the same, the derivation and reasoning required for case number 2 is quite a bit more complicated. Remarkably, this same result for HTT in terms of the source motion can be applied for case number 3 if it's interpreted properly. This is the case in which the gravitational fields may be strong, but the motion is slow. Now, the fourth case, in which we have strong gravity and fast motion, requires a fully nonlinear treatment of the source. Currently, this can only be done using a numerical code to solve the full Einstein equations. Numerical relativity is, of course, a big subject, and I won't have any more to say about it in this lecture. Now, before I get into the details of the derivation of this formula for case number 1, there's one more concept that I need to discuss, and that's the implications of the slow motion assumption. Notice that cases 1, 2, and 3, in which this formula holds, all assume that the source motion is slow compared to the speed of light. So if we have a compact source of size L, the only thing the matter can do in this compact region is oscillate back and forth or circulate around. So the typical velocity will be roughly 2 pi L over the period of the motion, and that's 2 pi L times the frequency of the motion. Now, it's the frequency of the source that determines the frequency of the gravitational waves. But the gravitational waves travel at speed c, So the frequency of the waves is c over the wavelength. So this is 2 pi L times c over the wavelength of the gravitational waves. Now let's define lambda bar as lambda divided by 2 pi. This is referred to as the reduced wavelength. So we see from this result that V is roughly LC over lambda bar, or equivalently, V over C is roughly L over lambda bar. So we see from this result that the slow motion assumption, V much less than C, implies that the size of the source is much smaller than the reduced wavelength of the gravitational waves. Now let's focus on the first case. That's weak gravity, slow motion, and negligible internal gravity, and derive the result for the metric perturbation in terms of the source motion. Since gravity is weak throughout space, we can use the linearized Einstein equations in Lorentz gauge. That's box h bar mu nu equals minus 16 pi t mu nu of eta. The box operator is, of course, just the wave operator, partial alpha, partial alpha. So each component of the trace-reversed metric perturbation satisfies a simple wave equation, and the solution should be familiar from electromagnetism. In that case, the components of the vector potential satisfy wave equations box A mu equals minus 4 pi J mu, where J mu is the charge current. The solution at some field point x and time t is given by an integral over the source, d3x prime, of the charge current at point x prime and at the retarded time t prime. So t prime is just t minus the magnitude of x minus x prime, all divided by x minus x prime, the distance between the source point and the field point. Let me draw a picture. So here's the source. These are the coordinate axes, the x, y, z axes. And this is a point in the source, which we label x prime. And this is the field point, or observation point, which we label x. And this distance is the magnitude of x minus x prime. I'll remind you that t prime is referred to as the retarded time. So the time t here is retarded or delayed from t prime by the light travel time between the source point and the field point. The equation for the trace-reversed metric perturbation has precisely the same form as the wave equation for the electromagnetic potential. So by analogy, we can immediately write down the solution, which is h bar mu nu at the field point x and time t is equal to 4 times the integral over the source, d3x prime, of t mu nu evaluated at the source point x prime and the retarded time t prime. So that's t minus magnitude of x minus x prime, divided by the distance x minus x prime. Of course, this same figure applies, showing the relationship between the source point and the field point. And it's important to note that this solution satisfies the Lorentz gauge. That's partial mu h bar mu nu equals 0. I'll leave the proof of this result as an exercise, but just note that the proof uses partial mu T mu nu equals 0. In other words, the statement of energy momentum conservation for the source. Now recall that we can determine the gravitational wave signal from just the space-space components of h bar mu nu. In other words, hij tt depends only on h bar ij, and of course the 0, 0, and 0i components of htt vanish. So let's just focus on the space-space components of h bar. We have h bar ij at the field point x and time t is equal to 4 times integral over the source of tij at x prime and t prime, divided by the distance between x and x prime. Now let's approximate this result for field points that are far away from the source. So here's the source, and we assume the coordinate origin is deep inside the source. Here's a source point, and the field point is very far away. In particular, we'll assume that this distance from the coordinate origin to the field point, we'll call that r, which is just the magnitude of x vector. We'll assume that r is much greater than the reduced wavelength of the gravitational waves. And because the slow motion assumption tells us that lambda bar is much greater than the size of the source, we can conclude that r is much greater than L. So in this picture, the distance of one reduced wavelength from the origin lies between the source and the field point. So this is the distance lambda bar, much less than r, but much greater than the size of the source. So with these assumptions, we're going to replace the magnitude of x minus x prime with r. And the way to justify those replacements is to carry out a Taylor expansion, first on the factor 1 over the magnitude of x minus x prime. This is approximately equal to 1 over r times 1 plus x hat dot x vector prime over r, where x hat is the unit vector in the direction of the field point. Now x vector hat dotted with x vector prime is on the order of the size of the source, so this is on the order of L. We can justify dropping this term and the higher order terms in the expansion since we're assuming L is much smaller than R, and we can approximate the factor of 1 over magnitude of x minus x prime with 1 over r. Now the distance between the source point and the field point appears not only in the denominator of this expression, but also in the argument of the stress energy momentum tensor through the retarded time. And for this appearance of x minus x prime, we need to be careful. Let's imagine expanding Tij, which is a function of the source point and the retarded time, in a Fourier series. So this is something like sines and cosines of omega t prime. But t prime is t minus the magnitude of x minus x prime. Now omega is 2 pi over the wavelength, which is 1 over the reduced wavelength. So Tij is roughly omega t minus the magnitude of x minus x prime divided by lambda bar. Now when we carry out the series expansion, we obtain sine omega t minus r over lambda bar plus x hat dot x vector prime divided by lambda bar. Now once again, x hat dot x vector prime is on the order of the size of the source, L. So since we're assuming L is much smaller than lambda bar, we can justify dropping this term and the higher order terms and approximating the retarded time t prime by t minus r. So by assuming that we're far away from the source, we can replace the magnitude of x minus x prime here and here with r and write the space-space components of the trace-reversed metric perturbation as hij bar of x and t equals 4 over r times the integral over the source d3x prime of tij of x prime and t prime evaluated at the retarded time, which is t minus r. This is a nice simple result that we can use to compute the space-space components of the trace-reversed metric perturbation in Lorentz gauge. We can then apply our prescription to convert this to the TT gauge. We drop the longitudinal part and remove the trace from the transverse parts. Keep in mind that this result applies only to case 1 sources. That is, sources with weak gravity, slow motion, and negligible internal gravity. For example, a rotating bar. I'll compute the gravitational waves from this source in detail in the next lecture, but for now notice that what makes this a case 1 source is that we assume that the motion is slow, so the outer edges of the bar are moving slow compared to the speed of light, and also that the internal gravity is negligible. In other words, the gravitational attraction between different parts of the bar is negligible compared to the internal stresses that hold the bar together. Remember, the space-space components of the stress-energy-momentum tensor are the stresses and momentum fluxes. So these are the material properties that enter into this formula for the gravitational wave signal. So we can see that this result does not apply to case 2 sources. For example, we could have a binary star system. Even if these are ordinary stars with weak gravity and slow motion, it's the internal gravitational attraction between the stars that keeps them in binary orbit. For this source, it's the gravitational stresses that play the role that the material stresses play for the case of the rotating bar. But this formula doesn't allow for gravitational stresses as a source, only material stresses. Remember from the earlier lecture on the energy and momentum of gravitational waves that the effective stress-energy momentum tensor for the gravitational field comes from the quadratic terms in the Einstein tensor. So the gravitational stress, which in that lecture would be denoted tau ij, is built from the terms in the expansion of the Einstein tensor that are quadratic in the perturbation h. But in deriving this formula, we use the linearized Einstein equations and dropped the quadratic terms in h. When we did that, we eliminated the possibility of allowing for internal gravitational stresses. This is why this result is only valid for sources with negligible internal gravity and is not valid for case 2 sources. Even for case 1 sources, like the rotating bar, this formula can be difficult to apply because the internal stresses of a source can be difficult to calculate. There is an alternative version of this result that is usually easier to apply. This alternative version uses the conservation of energy momentum partial mu t mu nu equals 0, which implies the following identity. Tij equals 1/2 partial 0 of t00 times xi xj minus 1/2 times partial k partial L of tkl times xi xj plus partial k of t ki xj plus t kj xi. I'll leave the proof of this identity as a practice problem. And now we can insert Tij into our formula for the trace reversed metric perturbation in Lorentz gauge. We have h bar ij of x and t equals 4 over r times the integral over the source, d3x prime, times Tij of x prime and t prime, evaluated at the retarded time, t minus r. Now we use our identity to replace Tij with the right-hand side, and notice Tij is evaluated at x prime and t prime, so we have to evaluate the right-hand side here at x prime and t prime. So for example, these time derivatives are with respect to t prime, and these x's are x primes. When we do that, these total derivative terms vanish because they integrate out to the boundary at infinity, but the source is compact. So the only term that contributes is this term involving second time derivatives of t00. So we can replace Tij with 1/2 partial 0 prime partial 0 prime of t00 as a function of x prime and t prime times xi prime xj prime. And now pull the time derivatives outside the integral and define ij of t prime as the integral over the source of t00 of x prime and t prime times xi prime xj prime. This is referred to as the second moment of the mass distribution. We can of course evaluate this at the retarded time by setting t prime equal to t minus r. Then our main result here becomes h bar ij of x and t equals 2 over r times the second time derivative of the second moment of the mass distribution evaluated at the retarded time. This gives us a way of calculating the space-space components of the trace reversed metric perturbation in terms of the mass distribution of the source. We can then apply our prescription for converting the trace reversed metric perturbation into the transverse traceless gauge. In fact, we can take this result one step further by writing HTT in terms of h bar and the projection operator that we defined earlier. So this is Pik Pjl minus 1/2 Pij Pkl times h bar Kl. And remember, Pij is equal to delta Ij minus k hat I k hat j, where k hat is the unit vector in the direction of propagation. Putting this together, we find HTT Ij of x and t equals 2 over r times the second time derivative of I bar Ij evaluated at the retarded time t minus r, where I bar is defined as Pik Pjl minus 1/2 Pij pkl times ikl. I bar is called the reduced quadrupole moment. So this is our final result, which we've derived in detail for any case number 1 source. That is, any source with weak gravity, slow motion, and negligible internal gravity. But in fact, this result holds for case number 2 sources as well. These are sources with weak gravity and slow motion, but non-negligible internal gravity. The way to see this is to repeat the analysis, including the quadratic terms from the Einstein tensor that give rise to the effective stress energy momentum tensor for the gravitational field. So to show this is true, we repeat the analysis with T mu nu replaced by T mu nu minus 1 over 8 pi times the quadratic terms in the Einstein tensor. This is sometimes denoted little t mu nu. With this replacement, all of the steps in the analysis go through to give us this same result. The difference being that the second moment of the mass distribution includes the gravitational part, little t00. So we obtain Ij equals the integral d3x of t00 plus little t00 times xi xj. But for nearly Newtonian sources with weak gravity and slow motion, this term can be dropped because little t00 is much less than big T00. So our results for HTT as well as for H bar hold for case 2 sources as well as case 1 sources. Although keep in mind that our earlier result for H bar Ij in terms of an integral over the matter stress, capital Tij, does not hold for case 2 sources. One last remark. Our final result for HTT also holds for case 3 sources. These are sources with strong gravity but slow motion. In this case, we can't express the reduced quadrupole moment as an integral over the source. Instead, we must determine I bar from the gravitational field in a region that's far from the source but not too far. In particular, we use the gravitational field at a distance r that's much larger than the size of the source but much smaller than the reduced wavelength of the gravitational waves. This is the same way that we determine the mass and angular momentum of the source, by analyzing the gravitational field in the far weak field region. In the next lecture, I'll work through some examples of gravitational wave sources. Before I finish, let me point out one mistake I've made in the terminology. The reduced quadrupole moment usually refers to the second moment of the mass distribution with the trace removed. What this is really the TT part of the reduced quadrupole moment. And this is usually denoted I bar ij sub tt.